All right, let's talk about algorithm design. We're not just going to go through a course syllabus today. No, we're going to build a strategic map to absolutely conquer it. If you've ever stared at a list of topics and just felt completely lost, well, you're in the right place. Let's jump in.
Oh man, does this sound familiar or what? We have all been there. It's that sinking feeling when the final exam is breathing down your neck and that mountain of material feels, well, impossible. That feeling of pure panic, that's our starting point.
But instead of panicking, we're going to get strategic. We're going to take that intimidating list of topics and turn it into a clear, easy-to-read map. A map that shows you the main roads, the shortcuts, and how every single piece connects to the others.
So first things first, we need to get the lay of the land. Think of this course not as a bunch of random problems, but as a gauntlet of challenges. Each one is designed to make you a sharper, more efficient problem solver.
Now, before we start exploring our map, we have to learn how to read its legend. And in the world of algorithms, that legend is all about one thing: efficiency. How do we even know if one solution is better than another? That's what we're about to find out.
So what even is an algorithm? When you boil it all down, it's just a recipe, a set of step-by-step instructions for getting something done. But the goal isn't just to find any recipe, it's to find the best, most elegant, and fastest one.
Okay, so how do we talk about what's fastest? We use this language called asymptotic notation, and the most famous one is big O. Think of it this way. We're not worried if one car is 5 seconds faster than another in a drag race. We care about what kind of vehicle it is. Is it a bicycle, a family car, or a rocket ship? Big O tells us if our algorithm is a bicycle or a rocket ship, especially when the input size gets huge.
And within that language, we usually look at 3 different scenarios. You've got your best case, which is, when everything goes perfectly, the average case, which is what you'll probably see day to day, and then there's the worst case. We actually focus on this one a lot. Why? Because if your algorithm can handle the absolute worst case scenario gracefully, you know you've got something solid and reliable.
And this chart right here shows you exactly why this matters so much. Just look at the difference. O of n scales nicely in a straight line. O of n log n is also really good. But that O of n square line, whoa. As the input n gets bigger, the time it takes just explodes. This visual makes it crystal clear that choosing the right approach is absolutely critical.
So, now that we know how to measure success, it's time to explore the main routes on our map. These are the big hitter strategies, the core design patterns that are going to form your problem-solving toolkit. First up is a classic: divide and conquer. The name really says it all. You take a big, messy problem and you break it down into smaller, simpler versions of the same problem. You keep breaking it down until the pieces are so tiny they're trivial to solve. Then you just stitch all those tiny solutions back together. And it's always the same simple 3-step dance. Step 1, divide the problem. Step 2, conquer the little subproblems. And step 3, combine the results. That's it. Simple, elegant, and unbelievably powerful. I guarantee you've seen this in action. Famous sorting algorithms like merge sort and quick sort, they're pure divide and conquer. And that lightning-fast binary search, same idea. It finds what you're looking for by just cutting the search space in half, over and over again.
Let's grab our next tool, the greedy method. This strategy is all about making the best possible choice right now, at this exact moment, without thinking about the future. At every single step, it just asks, what's my best move, and does it.
Now, this live-in-the-moment strategy doesn't work for everything, but when it does work, it's often the simplest and fastest way to get the job done. It's perfect for things like finding the shortest path in a network using Dijkstra's algorithm.
And next up, we have dynamic programming, or DP. Now, like divide and conquer, it also breaks problems down. But here's the secret sauce. DP is smart. It realizes when it's about to solve the same little subproblem for the 10th time. So instead, it solves it just once, then saves the answer in a table to look up later. It's all about remembering what you've already done to save a ton of work. So this is a big one, because people get greedy and DP mixed up all the time. Here's the key difference. A greedy algorithm makes a choice, commits to it, and never looks back. Dynamic programming is more patient. It explores all the options at each step to build up the perfect solution from the ground up.
And this is the classic example that makes it all click. For the fractional knapsack, where you can take, say, half a gold bar, the greedy approach of just taking the most valuable stuff per pound works perfectly. But for the 0-1 knapsack, where you have to take the whole item or leave it, well, for that you need the more careful, exhaustive approach of dynamic programming.
Okay, we've traveled the main highways on our map. Now it's time to venture into the trickier terrain, the labyrinth of problems that are so hard, just trying to brute force them will get you nowhere.
First up in this part of the world is backtracking. The best way to think about it is like you're in a maze. You pick a path and you go down it. If you hit a dead end, what do? You turn around, you backtrack to the last choice you made, and you try a different path. That's exactly what this algorithm does.
And this kind of systematic trial and error is perfect for solving complex puzzles. You know, like the classic n-queens problem. How do you put n queens on a chessboard so none of them can attack each other? Backtracking will explore every possibility, one move at a time, until it finds a solution.
Which brings us to one of the most famous problems in all of computer science, the traveling salesman problem. The question sounds so simple, right? But as you add more and more cities, the number of possible routes just explodes into astronomical numbers. It's incredibly hard to solve.
So how on earth do you tackle something like that? Well, you use a really clever technique called branch and bound. It still explores possible routes, but it's much smarter than just checking everything. It keeps track of the best solution it's found so far. And then, if it starts exploring a new path and realizes, hey, there's no way this path will end up being better than the one I already have, it just cuts off that entire branch of possibilities and saves a massive amount of time.
All right, we've built our map, we've explored the main roads, and we've navigated the tricky back alleys. So how do you actually use all of this to ace that exam and just become a better problem solver in general?
Here it is. This is the absolute key. Stop trying to memorize dozens of individual algorithms. Instead, learn to recognize the underlying pattern of the problem in front of you. Ask yourself, can I break this down? Should I make the best choice right now? Do I need to remember past results? Recognizing the pattern is what tells you which tool to pull from your toolkit.
See? That syllabus isn't a scary, intimidating list anymore. It's a landscape, a world of challenges just waiting for you to solve them. You have the map, you've got the tools. The only question left is, where are you going to start?